This video is part of the series to accompany discrete mathematics and functional programming. I'm Thomas Van Drunen. Specifically, this video is the first of a pair of videos on material from sections 1.4 and 1.5. Together, these two videos, and these two sections in the book, teach operations that can be performed on sets, assertions or propositions we can make about sets, and how to verify these propositions using visual arguments. On one hand, most of you are still getting used to the concept of a set as a mathematical object, so this is still pretty basic. On the other hand, everything we do here is looking ahead to one of the principal goals of this text, learning to write proofs. Thus, verifying assertions about sets is a crucial pre-proof writing game in the sequence of things we'll be doing in this course. This video and section 1.4 are mainly about the set operations. The next video, in section 1.5, demonstrate the visual representation. Now, we are learning a sort of arithmetic on sets, and to understand this right, we'll use analogies from plain old arithmetic. Consider the 6 arithmetic operations on this slide here. I hope you can sense there is an important difference between the top 3 and the bottom 3. There are different ways to describe the difference. If you wanted to cast it in computer programming terms, the top 3 have a different type from the bottom 3. After covering symbolic logic, we might say that the ones in the bottom are propositions, whereas the ones in the top aren't. But since we haven't introduced either of those things yet, let's consider it both in terms of what they produce and in what they are grammatically. The top 3 each produce a number as their result. So 5 plus 3 produces 8, 12 minus 7 produces 5, etc. This means that in terms of a mathematical sentence, they are equivalent to nouns, so they in fact are not mathematical sentences. The bottom 3, by contrast, do not produce a number. They are either true or false. Maybe you've noticed that the last one on the lower right happens to be false. Grammatically, they are equivalent to sentences, declarative sentences to be precise. And here's why that's important. The set operations we'll introduce here also fall into 2 categories. Some set operations produce new sets as the result, as plus and minus result in numbers. Others are going to be sentence making. They'll provide a main verb for assertions about sets. So we have 2 main sentence-making operations for sets. First of all, the axiom of extensionality that we saw last time gave us what we could consider an equals operation on sets. It gave us a way to talk about what it means for 2 sets to be equal to each other. 2 sets A and B are equal if they have all the same elements as each other. The second primary set-making operation is the subset operation. A set B is a subset of a set A if every element in B is also an element in A. You can see it written here symbolically and visually in a diagram. And by the way, if you didn't know before, these circle diagrams that we saw last time, and we'll see throughout this in the next video, have a name. We call them Venn diagrams. Notice that if 2 sets are equal to each other, then the subset definition applies. If B is equal to A, then it qualifies for the definition of subset. B is also a subset of A. Another way to put that is that any set is a subset of itself. And you can kind of sense that with the line that is at the bottom of the subset symbol. It should remind you of arithmetic operations like less than or equal to or greater than or equal to. In fact, along those lines, if B is a subset of A but is not equal to A, that is, if everything in set B is in set A, but at least one element in A is not in B, then we say that B is a proper subset of A. The symbol for that is just like the symbol for subset, but without the line underneath. We won't use the idea of proper subset very much. That's because most interesting things we could say about subsets are true even if the sets are equal. Note in passing that we could turn this definition around and talk about supersets and proper supersets. But again, we won't make much use of the idea of a superset. The only important thing to notice is that all of these are analogous to less than or equal to, less than, greater than or equal to, and greater than. The symbols were, of course, chosen to reflect this analogy. Now let's talk about set operations that make new sets. First, the union operation. The union of two sets is the set containing all of the elements of either set. You can remember this by noting that we are uniting the two sets together, and moreover, the symbol looks like a U for union. Look at the definition of A union B on the left, and remember how set notation works. In the given examples, note that sets may have some overlap, as 2 and 3 are elements of both set 1, 2, 3 and 2, 3, 4. They may have no overlap, as the sets 1, 2 and 3, 4 have none. Or one set may be completely a subset of another, as the set 1, 2 is a subset of the set 1, 2, 3. All of that really doesn't matter. The union comprises any element that is in one set, the other, or both. So the union of set 1, 2, 3 and set 2, 3, 4 is a set 1, 2, 3, 4. Likewise, the union of set 1, 2 and set 3, 4 is the set 1, 2, 3, 4. The union of the set 1, 2 and the set 1, 2, 3 is the set 1, 2, 3. The Venn diagram is simple. The shaded area shows the union of A and B, so all of A and all of B are shaded. Now, the companion operation to union is called intersection. The symbol for it is the union symbol turned upside down. The intersection is the set of elements that are in both sets. Notice in the Venn diagram that the overlap of the two circles is shaded. If A is the set 1, 2, 3 and B is the set 2, 3, 4, then the intersection of A and B is a set of elements in both, namely 2, 3, the only two elements that are in both A and B. If A and B have nothing in common, such as the set 1, 2 and the set 3, 4, then their intersection is the empty set. Notice that does not mean that there is no intersection. They have an intersection, all right, just that that intersection is empty. Finally, if A is a subset of B, as the set 1, 2 is a subset of the set 1, 2, 3, then the intersection of A and B is identical to A. It is the set 1, 2 in this case. The third common set operation is a little trickier. The difference between two sets, A and B, is the set of those elements in A that are not in B. This is analogous to subtraction in arithmetic, but of course it's not exactly the same thing. Take a look at the diagram first. A minus B is the shaded area. It looks like A with a bite taken out of it, namely that part where A overlaps with B. In other words, everything in the intersection is gone. Now look at the examples. The set 1, 2, 3 minus the set 2, 3, 4 gives us the set containing just 1, since that's the only thing in the first but not in the second. The fact that 4 is in the second set doesn't matter. If two sets have an empty intersection, as the set 1, 2 and the set 3, 4 do, then the difference is identical to the first set. In this case, it's just the set 1, 2, since there is nothing in the second set that is in the first set for us to remove. If A is a subset of B, as 1, 2 is a subset of 1, 2, 3, then A minus B is the empty set. There is nothing that is in A that is not in B. The thing to keep in mind with set difference is that order matters. Not the order of elements in the sets, of course, but the order of the sets themselves. Unless A and B are equal, A minus B is going to give you a different result from B minus A. Just like the arithmetic subtraction operation, difference is not commutative. Putting them all together, union is the set of elements that are in either set. Intersection is the set of elements that are in both sets. And difference is the set of elements that are in the first but not in the second. We're almost done. 3 more points to draw your attention to. First, sometimes it's useful to give a context for the sets we're talking about. It's unlikely that we would ever be interested in, say, the union of the set of Kia car models and the set of kinds of skin rashes. Usually, any use of sets implies that there is what we call a universal set. That is, the set of anything we could be possibly talking about in this context. We denote the universal set with a script U, as you see here. Of course, that font that it's drawn from is a different kind of script letter from the script letters we use to symbolize the number sets we saw last time. For our purposes, the universal set is mainly useful for defining other things more precisely. For example, and this is the second point that I want to make in closing, is that we sometimes will need to talk about the complement of a set. That is, the set of everything that is not in a given set. So see the definition here of the complement of a set X. It is the set of everything, little x, that is in the universal set, but is not in set big X itself. The set of everything in the universal set that's not in the set we're taking the complement of. In the diagrams, we'll draw the universal set as a rectangle framing everything else in the diagram. So you can see that in this diagram where the universal set makes up the background. Notice in this example that the complement of X is shaded. Namely, everything is shaded except for X itself. That shaded area then is the complement of X. Complement, of course, is analogous to the negative sign in arithmetic. For example, both complement and the negative sign are unary operations. That means they take only one argument, as opposed to union, intersection, and difference that each take 2 arguments, just as addition, subtraction, multiplication, and division do. The third and last thing to mention this time is that these operations can be combined arbitrarily, just as arithmetic expressions can be. Hence, we can talk about the complement of quantity x minus the union of y and z. So complicated expressions like that are hard to articulate in English, but they make perfect sense symbolically. Now take a moment to detangle this particular expression and convince yourself that the Venn diagram shown here indeed captures that set, the set produced by that expression, accurately. That completes our tutorial of basic set operations. Next time we'll start making assertions about set properties, similar to the laws of arithmetic that you may remember, or like theorems from high school geometry. We will see how a series of Venn diagrams can be used to verify the assertions we're going to make. And in fact, this will be a warm-up for the proof writing that we'll get into starting in Chapter 4.